Today, on how it's made. Corn tortillas. Crankshafts and camshafts. Bush planes. And aluminum bike wheels. The corn tortilla is the original flatbread, invented, legend has it, thousands of years ago by a Mayan peasant to feed his king. A royal appetite may have been the inspiration for this unleavened creation, but it soon gained mass appeal and became a staple of the Mexican diet. The corn tortilla has been popular for thousands of years. In the last century, demand has grown as people in many countries acquire a taste for Tex-Mex cuisine, like tacos, enchiladas, and nachos. Corn tortillas are now mass-produced in factories, and the process starts with grade A corn, dehusked and removed from the cob. There are millions of kernels in one truckload. They unload onto an elevator that takes them several stories up to deposit them in a silo. They're stored here until the factory is ready to start production. They then spill out of the silo and into big steel cooking vats. A worker adds water, completely immersing the corn. He activates a steam injection heating system. And as the temperature rises, he tosses in numerous scoops of powdered limestone. It acts as a preservative and helps soften the kernels during cooking. As they soften, the outer skin or pericarp loosens, releasing starch and creating a foamy effect. After 45 minutes, they turn off the heat and the corn steeps for 8 hours. With the kernels softened even more by the long soak, it's time to wash off a lot of the loosened pericarp. A little pericarp still clings to the cooked corn, but that's part of the plan. It will act as a bonding agent when the corn is shaped into tortillas. The corn now funnels into a spiraling blade that delivers it to a grinder. They add water and a preservative. The auger moves the ingredients between two volcanic stones that grind everything into a corn mash. The mash has a grainy texture similar to couscous. That changes when they press it through an extruder. The extruding kneads it into a dough called masa. As the masa exits the machine, it's collected by a worker. He transfers the corn dough to a machine called a pre-sheeter. Here, automated paddles push the masa between two sets of rollers. The rollers press it into a thick sheet. The sheet of dough travels through another machine called the sheeter cutter. In this machine, more rollers squeeze the dough paper thin as a die cuts out round tortilla shapes. They roll and cut 84,000 tortillas an hour on the sheet cutter. Another big roller takes up the matrix to be reused in the next batch of dough as the cut tortillas head into the oven. Once inside, the tortillas zigzag back and forth on 3 tiers of conveyors. The lowest tier has the lowest temperature, and the top tier the highest. This 3-tiered approach gradually bakes the tortillas in just 21 seconds, producing corn tortillas with just the right consistency. A vacuum system suctions the tortillas to the next conveyor to keep them from falling off as they now head to a cooling station. Here, the tortillas again move to and fro, this time on 9 conveyor tiers to cool. From a handful of corn kernels to a piece of round unleavened bread. Once the corn has been cooked, the transformation happens in just minutes. Whether the tortilla is made from white corn, yellow corn, or dyed other colors, the taste will be much the same. Exiting the cooling zone, the tortillas move into lanes. These lanes orient the tortillas in single file so they land in slots and stack up neatly. A sensor keeps a running count, and when there's a pile of 40, a trapdoor opens and sends them to the packaging line. These tortillas are now ready to add a little Latin sizzle to the menu. Packaged in stacks of 80, they're headed for restaurants and cafeterias. Fried, steamed, or just warmed in the oven, when they start adding the fillings, things could get spicy. In every vehicle, there are rotating shafts. The crankshaft converts the piston's vertical action into the circular motion that drives the wheels. At the same time, the camshaft turns to open and close airflow valves. These precision parts are behind every successful startup. A life on the road can be tough, and a good crankshaft has to keep on turning when the engine is under stress. The crankshaft starts with a forged steel shape. A computerized blade shaves off excess metal from sections called counterweights. They offset the load of the engine's pistons and connecting rods, and this process slims them down to create a balance. A computerized drill bores holes into one of the bearings to reduce the overall weight. Next, a worker removes marks the computerized tools have left on the metal. He sands the entire crankshaft. The surface must be completely flawless for it to operate smoothly. Fine glass beads blast the part as it revolves in a rotisserie-like device to knock off sharp edges and give the crankshaft a consistent finish. The crankshaft then spins in a lathe as a blade slices away a precise amount of metal from each of the counterweights. This machining provides enough clearance for the engine's pistons and rods to function. The crankshaft then takes another spin in a device that has sensors to detect any imbalance. It calculates that just over 29 grams of metal still needs to be removed. Once the adjustment has been made, he measures the degree of straightness. If it's off even slightly, he corrects it by applying pressure with a press and tapping a special radius chisel. He then measures again to confirm he's done an even job. On the left is a crankshaft that hasn't been balanced or straightened. On the right is one that has. Production now moves to the engine's other rotating shaft, the camshaft. Machining transforms a steel billet into the basic shape. Like the crankshaft, this camshaft will need a lot of fine-tuning. An automated tool first etches the part number and date onto one end, and then they get down to the precision work. The camshaft must also be completely straight, so the technician measures it from one end to the other and makes adjustments where needed. Next, he selects a master template of a camshaft lobe and places it in a grinding machine. This master is the pattern to be copied by a grinding wheel. Once it's been locked in place, he activates the grinder. It carves into the camshaft as it rotates and rocks back and forth in the machine. The grinding wheel moves down the camshaft to shape all 16 lobes to the exact contours of the template. This is how the camshaft looked before the master grinding, and after. Next, a computerized probe measures the profile of each lobe and confirms that the dimensions and lift are identical. At the next station, the camshaft spins to allow a worker to completely coat the journal bearings with a blue dye. The dye masks the bearings to keep them smooth, while the rest of the camshaft is being parkerized. Parkerizing will give the camshaft an etched finish, which protects against wear. They start with a quick rinse. Then they plunge the camshafts into hot phosphorus acid. The acid microscopically etches the metal, while other chemicals in the bath add a thin graphite coating. They rinse the residue. After the finish has dried, a worker buffs the journal bearings as the camshaft spins. This completely rubs off the blue dye and polishes the metal. He then wipes down the entire camshaft with a dry rag. He places the camshaft on a perforated metal shelf and floods it with oil. Some oil drains away, but a residue clings to the part, and that residue will prevent rusting. Once packaged, this rotating shaft is on its way to a garage or car factory, where ultimately it will do its part to help set the wheels in motion. Bush planes are designed to fly in and out of remote areas. They're engineered to be able to take off and land on short runways. They can also be outfitted with floats to be able to land on water or skis to land on snow. Some are made of metal and others of tube and fabric construction. A bush plane starts out as a design on paper. This company handcrafts four-seater tube and fabric models. The tubes forming the airplane's skeleton, the fabric its skin. Welders construct a tubular frame for the fuselage, the plane's main body. The tubes are chromoly, a type of steel that contains chromium and molybdenum, which make it stronger than standard steel. Machinists make the aluminum fuel tank components and prepare the landing gear. Here, they're threading the axle for the tail wheel, a small rugged wheel at the back which helps steer the airplane on the ground. The landing gear consists of this tail wheel and two bigger wheels at the front. They all have large, low-pressure tires, which enable the plane to take off and land on rough terrain. Workers spray aluminum pieces called ribs and spars with anti-corrosion paint, then rivet them together to build the internal structure of the wings. Using a crimping tool, they make tiny indentations in the ribs to perfect the alignment. Then they rivet on a skin of aluminum panels, about a ½ millimeter thick in most areas. They construct the wings' hinged surfaces, the flaps and ailerons, the same way. The factory's paint shop sprays the wings, flaps and ailerons with highly durable urethane paint, and the fuselage frame with powder coat paint, which is then baked on for extra durability. Now for the meticulous job of applying the fabric skin. The material is heat-shrinkable polyester, commonly used in the aircraft industry because it's thin, lightweight, and exceptionally strong. Workers brush an adhesive similar to contact cement onto the painted tubing, then adhere the fabric, working around the frame section by section. Once the fuselage is completely covered, they run a hot iron over the fabric. This shrinks it taut around the framework. After letting the adhesive dry for a couple of hours, they take strips of fabric, coat them with a urethane-based adhesive, and reinforce the seams. It's the same construction process for the tail components. At the front of the fuselage now, they install the pedals which control both the brakes and the rudder, which moves the tail from right to left. Then the cockpit instrument panel, a thin sheet of aluminum with laser-cut openings for all the flight instrumentation. Next, two linked control yokes. They move a series of chains which maneuver certain components, such as the aileron control sprockets. Mechanics ran the fuel lines and most of the wiring within the fuselage frame prior to the fabric application. Now they install a stainless steel firewall between the cockpit and the engine. This seals the cockpit from engine heat, noise, and exhaust gases. After installing the landing gear, brakes, and windshield, workers mount the engine and exhaust system. Next, the plane's aluminum propeller. Other workers are busy installing the fuel tanks inside the wings. The fuselage now goes to the paint shop. When it comes back, workers bolt on the wings, supporting them from underneath with steel wing struts. The wings on a bush plane are positioned higher than those on other types of aircraft to give the pilot better ground visibility. After rigging up the flight controls and installing the interior trim, workers install the doors, plexiglass windows, and cockpit seating. Each bush plane is inspected at every stage of the production process. When it's completed, it undergoes a nose-to-tail final inspection, and then a company pilot takes it out for a test flight. A serious cyclist won't pedal just any bike. It's got to have wheels made of strong yet lightweight materials, such as carbon fiber or aluminum. Advanced bicycle wheels have tubing and spokes shaped as aerodynamically as possible to lower wind resistance. These elite-level racing wheels are made of aluminum. They're designed to generate a smooth ride with optimum responsiveness to the rider's acceleration. The starting material? Long, straight tubes of extruded aluminum, pre-shaped with the wheel rim profile. Workers load one extruded tube at a time into a metal bender. The machine coils the tube around and around, forming 4 connected rims. After measuring to ensure the diameter is exactly what it should be, they mount the coiled tube onto a cutter. With a single downward slice, it separates the 4 rims. They fuse the cut ends later on. First, the rims need a bath in a tank of acid. The acid removes dust and other contaminants and etches the surface of the metal, both of which help ensure full adhesion of the anti-corrosion coating they later apply. Next, a multi-phase heat treatment process. This restructures the aluminum molecules, making the metal harder and stronger. They join the 2 ends of the rim by riveting on an aluminum connector tab. Then they weld the joint to reinforce it. Using a sharp, vibrating cutting tool, a computer-guided machine smooths the weld line until it's nearly invisible. This makes the rim appear seamless. Now for that anti-corrosion coating. The process is called anodization. In a tank, they plate the aluminum with a protective chemical, using an electrical charge to draw the coating particles onto the rim surface. For this model, the anodized coating is black. However, there are several color choices. Next, a computer-guided machine shaves off a minute amount of anodized metal from nearly a third of the rim's surface. This creates a smooth, perfectly flat area for the brake pads to grip. The next computer-guided machine drills holes for the tiny aluminum nipples, which hold the aluminum spokes to the rim. Now it's time to assemble the wheel, a manual task entrusted to specialized bicycle technicians, as it requires a level of craftsmanship no machine can perform. The first technician inserts a spoke into each slot of a carbon fiber and aluminum flange, part of the hub at the center of the wheel. Once every spoke is in its respective spoke seat, as it's called, he sandwiches them with a locking ring. Now for the rim end of the spokes. The next technician places a small steel plug inside a spoke nipple to make it magnetic. Then she puts the nipple into the rim and, using a magnet, draws it to a spoke hole, then through the hole towards the inside of the wheel. Then she removes the steel plug and inserts the free end of a spoke into the nipple. She repeats the procedure for each spoke hole. This is known as lacing the wheel. The next technician holds each spoke steady while tightening its nipple with a spoke wrench. Tightening the nipple straightens the spoke. The process of perfectly aligning the wheel by straightening every spoke is called truing the wheel. This gauge tells him when the wheel is finally trued. For quality control assurance, this robotic machine inspects each spoke and makes any necessary tensioning adjustments. Depending on the model, a high-end bicycle wheel can have anywhere from 10 to 46 spokes. Different spokes for different folks.